this video is actually going to be a combination of 4 sections, sections 2.5 to 2.8, and it's on postulates, theorems, and proofs.
Our first vocabulary word is a postulate. It is sometimes seen as an axiom, though that term is very out of date and won't be used in this class.
A postulate is a statement that is accepted as true without proof. So some examples of postulates in geometry are points, lines, and planes. We accept those definitions as true. We just know that they are true. We don't have to prove them. So when we talk about postulates, that leads us into what we call proofs. And a proof is a logical argument in which each statement you make is supported by statements accepted as true. So we come up with a new hypothesis and we prove it by using other definitions. So how we prove things is by using deductive arguments, which is a logical chain of true statements. One type of a proof is a paragraph or informal proof, where you just write a written explanation that justifies your conjecture. That is what we are going to do for the most part in this geometry class. We will not be writing paragraphs per se. We will be doing more informal proofs where you have to justify every step. It's not even just about showing your work. It's about knowing the definitions about why what you are doing is true. Then we have what are called 2-column or formal proofs, and they contain statements and corresponding reasons organized in 2 columns. They're much more formal, hence the term of formal proof, and the organization is much more important. We will explore these, but we will not do a tremendous amount of work with them in this geometry class. Once we prove something, that gives us a theorem. And a theorem is a statement or conjecture that has been proven. Once it has been proven, we can use it as a statement in other proofs. So once we take our hypothesis and we prove it, that is what gives us theorems. So this slide is a review of properties of real numbers that you should have learned in Algebra 1 and Algebra 2. I would suggest reviewing them. I am posting a copy of this PowerPoint as a Google slide, so you do not have to copy all of these, but I would read through them to make sure that you are familiar with them. These are our algebraic property, and many of our theorems that we develop are going to be based off of these algebraic properties of equality. So here we have our first postulates about points, lines, and planes. For through any 2 points, there is exactly 1 line. We already learned that in chapter 1. We are just putting it into more formal language. Through any 3 non-collinear points, there is exactly 1 plane. We already learned that information in chapter 1. All we are doing is putting it now into if-then format. So again, I would suggest you review these
And make sure you are familiar with
their definitions. But I'm never going to ask you, what's postulate 2.1? I'm going to say, how many points define exactly 1 line? And I want you to know 2. So you need to know these concepts, but you do not need to memorize the numbers that are attached to them. Here are more concepts that we have already learned, just put into if-then statements. So if 2 lines intersect, then their intersection is exactly 1 point. If 2 planes intersect, then their intersection is a line. We have already learned this information. We are just rewriting these statements in a formal manner. Again, if you learned it in the first chapter, you know it in the second. If you struggled in the first chapter, this is a way for you to learn that material before we move on. The midpoint theorem states if M is the midpoint, then segment AM is congruent to segment MB. These lines mean that they are congruent, and if they are congruent, then they have equal measures. Here's an example that uses some of the theorems and postulates that we just reviewed. Determine whether the statement is always, sometimes, or never true. Plane A and plane B intersect in exactly 1 point. So you would review the theorems and postulates that we just got, and we know that planes intersect in exactly 1 line, so this will never be true.
because by definition, planes intersect in 1 line.
Here is another example. Determine whether the statement is always, sometimes, or never true. Point N lies in plane X, and point R lies in plane Z. You can draw only one line that contains both points N and R. So remember our definition, remember our postulate, that through any 2 points there is exactly one line. So that will be always. And that is why you have to remember that through any 2 points there is exactly one line, not that it's 2.1 or 2.2. Just that through any 2 points there is exactly one line, even if they are not on the same plane. The ruler postulate just states that if we can put a number line on a ruler, then we can match up numbers to points, and we can get measures of lines. The segment addition postulate allows us to add, and we've again reviewed this before, allows us to add 2 parts and get the whole. But this is more specific because it tells us that the points must be collinear and that B must be between A and C, and then we can
Add the 2 parts to get a whole.
Here are properties of segment congruence. So this goes back to those algebraic properties. The reflexive property is any segment is congruent to itself. The symmetric property tells us that it doesn't matter which segment comes first. They are congruent no matter what. And the transitive property is probably my favorite property of congruence. I know it sounds weird to have a favorite property of congruence, but it's basically saying if AB is congruent to CD and CD is congruent to EF, then AB is congruent to EF, meaning if the 2 middle parts match up, we can just say the first and the third match up as well. So it's similar to the law of syllogism from the last video in that if the last part of the first one is equal to the first part of the second, you can cancel them out. So again, the transitive property allows us to compare 3 different things that are congruent. The protractor postulate we already discussed. It states given any angle, the measure can be put into a 1-to-1 correspondence with real numbers between 0 and 180. So this just allows us to use the protractor, which allows us to review the angle addition postulate, which was in a video at the beginning of chapter 2, which again states that the 2 smaller angles add up to the larger one. Here is an example to review this topic. The measure of angle 1 plus the measure of angle 2 is equal to the measure of angle JKL. So to find the measure of angle 1, you would take 162 and subtract 58, and that would give you 100, and that would give you 104. Here are the supplement theorem. Again, we did this in a video earlier. If 2 angles form a linear pair, then they are supplementary. The complement theorem states if the non-common side of adjacent angles form a right angle, then the angles are complementary. So again, we learned this in a previous video. So here's a real-world example. The diagram shows one square for a particular quilt pattern. We know that the measure of angle BAC is equal to the measure of angle DAE, and we know that they are both 20 degrees. So I know that this is 20 and this is 20. And I know that BAE, or the whole thing, is a 90-degree angle, and I want to find the measure of this angle. So I would simply take 90 minus the sum, and therefore the answer is 50. So the measure of angle CAD is 50 degrees. Again, the same way that we had the reflexive, the symmetric, and the transitive property of segment congruence, we have the same idea with properties of angle congruence. They're exactly the same thing, except instead of segments, we can say that angle 1 is equal to itself. If angle 1 is equal to angle 2, then angle 2 is equal to angle 1. In the transitive property, if angle 1 is equal to angle 2, and angle 2 is equal to angle 3, well, we know that angle 1 is equal to angle 3, and we can just leave 2 out. Congruent supplements theorem is actually new, so hopefully if you've tuned out, you're tuning back in at this point. What this is saying is that angles supplementary to the same angle or to congruent angles are congruent. So angle 1 and angle 2 add up to 180 degrees.
And angle 2 and angle 3 add up to 180 degrees.
And that means that angle 1 will be the same measure as angle 3. It's similar to the transitive property, except here they're not equal, they add up to the same thing. And it makes sense if we think about it. If angle 1 is 110 degrees, then we know, and these two are supplementary, then we know that angle 2 is 70. If angle 2 is 70, and angle 2 and angle 3 add up to 180 degrees, then that makes this 110 degrees, and therefore they are equal. The same is true about congruent complements theorem, except that we are using that they add up to 90. So if angle 4 is 30 degrees, and angle 50 would then be 60 degrees, and angle 5 and 6 are complementary, then this has to be 30 degrees as well. And we can see that angles that are complementary to the same angle are congruent to each other.
We have already learned about the vertical angles theorem and know that vertical angles are congruent. Remember that matching arcs are congruent.
Here are right angle theorems. So perpendicular lines intersect to form 4 right angles. We knew that perpendicular lines make right angles, but because they are vertical, if this one's 90, then this one's 90, then they're all 90. So if one angle is perpendicular, they are all perpendicular. We also know, since all right angles are 90 degrees, that all right angles are congruent. We know that perpendicular lines form congruent adjacent angles because if this is 90 degrees, then these are 90 degrees, which means that they are congruent, and adjacent means that they are next to each other and share that line. If two angles are congruent and supplementary, then each is a right angle. So the reason that we say that if they're congruent and supplementary, because if they're supplementary, they have to add up to 180 degrees. And the only way to get them to be congruent would be if they were both 90. Therefore, this theorem says that if they are congruent and supplementary, they're right angles. This is saying if they're a linear pair and they're congruent, then they're right angles because these still have to add up to 180 degrees. We are going to do examples where we use this information to find missing measures. It is very important that you understand all of the theorems presented. If you have any questions, please bring them to class.